Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night, but probably won't. The observable universe contains approximately 2 trillion galaxies. That's 2,000 penthousands galaxies, each a swirling island of hundreds of billions of stars. And each of those stars potentially hosts planets, moons, asteroids, comets, and perhaps even life. Think about that for a moment. 2 trillion galaxies. It's a number so large it's essentially meaningless to our brains, which evolved to deal with quantities like 3 berries or 10 fingers. To truly grasp the scale of the universe, we need to abandon our everyday intuition and embrace the mind-bending concepts of cosmology. And that's what we're going to do in this series. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Chapter 1. The Observable Horizon, Why We Can Only See So Much. By the end of this chapter, you'll understand why the universe has a horizon similar to Earth, how the expansion of space limits our view, and the mind-blowing implications for what might lie beyond. Let's start with a question that sounds simple, but has a profoundly complex answer. How big is the universe? The immediate intuitive answer might be, well, it's everything. And while that's technically true, it's not particularly helpful. The real question is, how much of the universe can we observe? Because that's a very different number. Imagine standing on a vast flat plain. As far as you can see, the plain stretches out in all directions. But your vision is limited by the horizon. No matter how hard you try, you can't see beyond that line where the Earth seems to meet the sky. The universe has a similar horizon, but for far more interesting reasons than the curvature of the Earth. Our cosmic horizon is determined primarily by 2 things: the age of the universe and the speed of light. The universe is approximately 13.8 billion years old. This means that the oldest light we can possibly see is light that has been travelling for 13.8 billion years. You might think that this means the observable universe is a sphere with a radius of 13.8 billion light years. But that's where the expansion of the universe throws a wrench into things. Here's the thing. The universe isn't just sitting there passively existing, it's expanding. And it's been expanding ever since the Big Bang. This expansion has a dramatic effect on how far light can travel to reach us. Imagine you're on a spaceship trying to reach a distant planet, but the space between you and the planet is constantly stretching. You have to keep speeding up just to stay in the same relative position. Light in the universe faces a similar challenge. As light travels through the expanding universe, the space it's travelling through is also expanding. This means the light has to travel farther than you might initially expect. Furthermore, the expansion of space also stretches the wavelength of the light itself, a phenomenon known as cosmological redshift. This is similar to the Doppler effect, where the pitch of a siren changes as it moves towards or away from you. But instead of the source moving, the space itself is stretching. The farther away an object is, the more its light is redshifted. Eventually, the redshift becomes so extreme that the light loses almost all of its energy and becomes virtually undetectable. So how far away is the edge of the observable universe? The answer is about 46.5 billion light-years in all directions. This gives the observable universe a diameter of roughly 93 billion light-years. That's significantly larger than the 13.8 billion light-year radius you might have initially guessed. This difference is due entirely to the expansion of space during the time the light has been travelling towards us. Think about it this way. Imagine a photon of light emitted from a galaxy shortly after the Big Bang. That photon has been travelling for 13.8 billion years. During that time, the galaxy that emitted the photon has moved farther and farther away from us due to the expansion of the universe. In fact, it's now much more than 13.8 billion light years away. The distance we measure is not the distance the photon travelled, that's always 13.8 billion light years, but the current distance to the object that emitted the photon. Now, this is where things get truly mind-boggling. What lies beyond the observable universe? The answer, frustratingly, is that we don't know for sure. It's possible that the universe simply continues on, looking much the same as what we can see. Galaxies, stars, and vast stretches of empty space. This would mean that the universe is much, much larger than the observable portion, perhaps even infinite. It's also possible that the universe beyond our horizon is drastically different from what we observe. The early universe may have undergone a period of extremely rapid expansion called inflation. Inflation could have stretched different regions of the universe to vastly different sizes and with vastly different physical properties. This means that beyond our observable horizon, there could be regions with different laws of physics, different types of particles, or even different numbers of spatial dimensions. We simply have no way of knowing because light from those regions will never reach us. The concept of a cosmic horizon also raises some profound philosophical questions. Are we in a special place in the universe? Is our observable universe representative of the universe as a whole? Or are we simply confined to a small, possibly atypical region of a much larger and more diverse cosmos? There's a subtle point that's easy to miss. The expansion of the universe isn't just about galaxies moving away from each other through space. It's about the fabric of space itself expanding. Imagine drawing dots on a balloon, then inflating the balloon. The dots move farther apart, but they're not moving across the surface of the balloon. The surface itself is expanding, carrying the dots along with it. Similarly, galaxies aren't just flying away from each other. The space between them is stretching, increasing the distance between them. This also means that the universe isn't expanding into anything. There's no outside of the universe. The universe is, by definition, everything that exists. The expansion is simply a change in the scale of the universe itself. So we've seen how the finite age of the universe combined with the speed of light and the expansion of space creates a cosmic horizon that limits what we can observe. But what about the very early universe? What can we learn from the light that has been travelling for almost 13.8 billion years? That leads us to the fascinating topic of the cosmic microwave background radiation, a faint afterglow of the Big Bang that provides a snapshot of the universe when it was only 380,000 years old. We'll explore that in the next chapter, so we've established that the universe, as far as we can see, stretches out for an almost incomprehensible fixed on 5 billion light years in every direction. But what about seeing further? Is there a way to peek behind that cosmic curtain to catch a glimpse of the universe when it was much, much younger? The answer, surprisingly, is yes. And it comes in the form of something called the cosmic microwave background, or CMB. Now, the name might sound intimidating, conjuring images of complex physics equations and mind-numbing data analysis. And, okay, there is some of that involved. But the basic idea is actually quite beautiful. Think of it as an echo, a faint but persistent echo of the Big Bang itself. To understand the CMB, we need to rewind the clock way back to a time when the universe was a mere infant, just 380,000 years old. Remember, the Big Bang wasn't an explosion in space, but an explosion of space, and in those early days the universe was incredibly hot and dense. Imagine a plasma hotter than the surface of the sun filling all of existence. Protons, neutrons and electrons zipped around in a chaotic soup, constantly colliding and interacting. Light, in the form of photons, couldn't travel very far without bumping into something. It was a cosmic fog, opaque and impenetrable. Think about trying to see through a dense fog on Earth. The light from a distant object scatters off the water droplets, blurring the image and making it impossible to see clearly. The early universe was like that, only on a truly epic scale. But as the universe expanded, it also cooled. And after about 380,000 years, something remarkable happened. The temperature dropped enough to around 3000 Kelvin, about 5000 degrees Fahrenheit, for electrons and protons to combine and form neutral hydrogen atoms. This event is known as recombination. Bit of a misleading term since they weren't really recombining, but combining for the first time. And here's the crucial part. Once the universe became neutral, photons could finally travel freely. The fog lifted. Light, which had been trapped for hundreds of thousands of years, was released into the cosmos. This is the light that we now see as the cosmic microwave background. It's the oldest light in the universe, a snapshot of the universe at a pivotal moment in its history. Think about that for a moment. We are literally looking at light that has been travelling across the universe for nearly 13.8 billion years. It's like receiving a message from the dawn of time. Now, because the universe has continued to expand since then, the CMB has been stretched and cooled. As we discussed in the last chapter, the expansion of space stretches the wavelength of light, shifting it towards the red end of the spectrum, redshift. This is why we see the CMB not as visible light, but as microwaves, a form of electromagnetic radiation with longer wavelengths. So how do we see microwaves? Well, scientists use specialized telescopes and instruments to detect this faint radiation. And when they do, they see something truly amazing. A map of the universe as it was in its infancy. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, variations of only a few parts in a million. These seemingly insignificant differences are actually incredibly important. They represent the seeds of all the structures we see in the universe today, galaxies, clusters of galaxies, and even the empty voids between them. Think about it like this. Imagine a perfectly smooth pond. If you drop a pebble into the pond, it creates ripples. These ripples, though small, can eventually lead to larger waves and disturbances. The tiny temperature fluctuations in the CMB are like those initial ripples, the seeds that eventually grew into the cosmic structures we observe today. These fluctuations are thought to have originated from quantum fluctuations during the period of inflation, a period of extremely rapid expansion in the very early universe. Remember inflation from the last chapter? It's coming up again. These quantum fluctuations, magnified by inflation, provided the initial density variations that gravity then amplified over billions of years, leading to the formation of galaxies and other structures. So by studying the CMB, we can learn about the conditions in the very early universe, test our theories about inflation, and understand how the universe evolved from a smooth, homogeneous state to the complex, structured cosmos we see today. It's like having a time machine that allows us to peer into the past and witness the birth of everything. But here's where things get even more interesting. The CMB also tells us about the composition of the universe. By analysing the patterns in the temperature fluctuations, scientists have determined that the universe is made up of approximately 68% dark energy, the mysterious force driving the accelerated expansion of the universe, 27% dark matter, an invisible substance that interacts gravitationally but doesn't emit or absorb light, 5% ordinary matter, the stuff we're familiar with, protons, neutrons, electrons, etc. Think about that for a moment. All the stars, galaxies, planets, and everything we can see with our telescopes accounts for only about 5% of the total mass energy content of the universe. The vast majority of the universe is made up of stuff we can't directly see or interact with. This is one of the biggest mysteries in modern cosmology. The CMB, therefore, is not just a snapshot of the early universe. It's also a window into the unknown. It hints at the existence of dark energy and dark matter, forces and substances that we are still trying to understand. And what about beyond the CMB? Can we ever hope to see further back in time to witness the very moment of the Big Bang itself? Well, that's a much tougher question. The CMB represents a fundamental barrier to our vision. Before recombination, the universe was opaque to light, so we can't directly observe anything that happened before that time using electromagnetic radiation. However, there are other potential messengers from the early universe that we might be able to detect in the future. For example, gravitational waves, ripples in the fabric of space-time, could potentially carry information from the very earliest moments of the Big Bang, even before recombination. Think about it like this. If light is like sound waves traveling through air, then gravitational waves are like vibrations traveling through the ground. They can penetrate obstacles that light cannot. Detecting these primordial gravitational waves would be an incredible feat, providing us with a glimpse into the universe at its very beginning. So while the CMB represents a cosmic horizon for light, it doesn't necessarily represent the ultimate limit of our knowledge. With new technologies and innovative approaches, we may one day be able to probe even deeper into the mysteries of the early universe. The universe is vast, ancient, and full of surprises. The cosmic microwave background is just one piece of the puzzle, but it's a crucial piece. It allows us to see the universe as it was in its infancy, to understand its composition, and to glimpse the forces that shaped its evolution. And perhaps, one day, it will help us answer the ultimate question: how did it all begin, and what, if anything, came before? But for now, let's shift gears slightly. We've talked about the observable universe, and we've looked at the oldest light we can see. But what about the stuff that we can't see? What lies beyond the cosmic horizon? Is the universe truly infinite? And if so, what does that even mean? We'll dive into those mind-bending questions in the next chapter. Okay, where were we? Ah yes, peering out at the cosmic microwave background, that ancient echo from a time when the universe was a mere infant. Think about that for a moment. The oldest light we can possibly see, a fundamental limit. But what about what lies beyond? What about the universe we can't see? That, my friends, is where things get really interesting. And, let's be honest, a little mind-bending. We've established that the observable universe is a sphere, roughly 93 billion light-years across. It's everything we can theoretically see, given the age of the universe and the speed of light. But that doesn't mean the universe stops there. Imagine you're standing in the middle of a vast ocean. You can only see as far as the horizon. Does that mean the ocean ends at the horizon? Of course not. The ocean stretches on far beyond what you can perceive from your limited vantage point. The universe is the same. Our observable universe is just our horizon. Now here's the kicker. We have absolutely no idea how big the entire universe actually is. It could be finite, but incredibly vast, far larger than we can fathom. Or And this is where many cosmologists lean. It could be infinite. Infinity. Just let that word roll around in your mind for a second. Infinity. What does it even mean for the universe to be infinite? Well, it means it goes on forever. No edge, no boundary, no ultimate wall to run into. If you kept travelling in one direction, you'd never ever stop. You'd just keep going and going and going. Pretty wild, right? But here's where it gets even wilder. If the universe is truly infinite, then it has some truly bizarre implications. Think about this. If the universe is infinite, and matter isn't created or destroyed, it just changes form, then every possible arrangement of matter must exist somewhere, out there. Let me repeat that. Every possible arrangement of matter must exist somewhere out there. What does that mean? It means that somewhere impossibly far away there's another Earth, and on that Earth there's another you, and that other you is reading this exact same sentence, thinking the exact same thoughts. And there's another Earth where you decided to become a professional interpretive dancer instead of reading about cosmology, and another where cats rule the world. Okay, maybe they already do. And another where the laws of physics are slightly different, leading to completely alien life forms and unimaginable landscapes. All of these possibilities and countless more exist in an infinite universe. It's a staggering thought, isn't it? A cosmic multiverse of infinite possibilities, all stretching out beyond our ability to ever observe them. Now, I know what you might be thinking. That sounds like science fiction. And you're right, it does sound like science fiction. But it's a direct consequence of the idea of an infinite universe, combined with the laws of physics as we understand them. Of course, we can't prove that the universe is infinite. It's incredibly difficult to test such a hypothesis. We're limited by our observable universe, and we can't exactly pop over to another galaxy to check if there's another version of ourselves hanging out there. Although, wouldn't that be a trip? So how do scientists try to figure out if the universe is finite or infinite? Well, they look for clues in the cosmic microwave background, CMB. Remember that afterglow from the early universe? It turns out that the CMB can tell us a lot about the geometry of the universe. There are three basic possibilities for the shape of the universe. Flat. In a flat universe, parallel lines stay parallel forever. This is the simplest and most likely scenario according to our current observations, and, surprise surprise, a flat universe could be infinite. Closed. In a closed universe, parallel lines eventually converge. Imagine the surface of a sphere. If you draw two parallel lines on a sphere, they will eventually meet at the poles. A closed universe is finite, but it has no boundary. You could travel in one direction forever, and eventually end up back where you started, like walking around the surface of the Earth. Open. In an open universe, parallel lines diverge. Imagine the shape of a saddle. An open universe is infinite and negatively curved. The CMB provides a way to measure the curvature of the universe. By analysing the patterns of temperature fluctuations in the CMB, scientists can determine whether the universe is flat, closed, or open. So far, the data overwhelmingly suggests that the universe is flat or very close to flat. This doesn't prove that the universe is infinite, but it certainly supports the idea. Another line of evidence comes from studying the distribution of galaxies in the universe. If the universe were finite and had a boundary, we would expect to see a non-uniform distribution of galaxies near the edge. However, so far we haven't found any evidence of such a boundary. Galaxies seem to be distributed more or less evenly throughout the observable universe. So what does all this mean? Well, it means that we're still a long way from knowing the true size and shape of the universe. but the evidence we have so far suggests that it could very well be infinite. Let's just pause on that for a second. An infinite universe. It's a concept that's almost impossible to grasp. Our brains, evolved to deal with the everyday world around us, struggle to comprehend something so vast and limitless. It challenges our very notions of space and time. But that's the beauty of cosmology, isn't it? It forces us to confront the biggest questions imaginable. It pushes the boundaries of our knowledge and understanding. It reminds us that we're just a tiny speck in a vast and mysterious cosmos. And that in itself is a pretty humbling and awe-inspiring thought. Before we move on, I want to address a question that I often get asked. If the universe is expanding, what is it expanding into? That's a great question, and it gets to the heart of how we understand the expansion of the universe. The key is to realize that the universe isn't expanding into anything. Space itself is expanding. Imagine you have a balloon with dots drawn on it. As you inflate the balloon, the dots move further apart from each other. But the dots aren't moving across the surface of the balloon. The surface of the balloon itself is expanding. The universe is similar. Galaxies aren't moving through space. Space itself is expanding, carrying the galaxies along with it. So that there's no need for the universe to be expanding into anything, it's just expanding. This can be a tricky concept to wrap your head around, but it's fundamental to our understanding of cosmology. Okay, so we've explored the idea of an infinite universe, and we've touched on the expansion of space, but there's another mind-blowing concept that we need to discuss: dark energy. Remember how we talked about the composition of the universe? How it's made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Well, dark energy is the mysterious force that's driving the accelerated expansion of the universe. We don't really know what dark energy is, that's the honest truth. It's one of the biggest mysteries in modern cosmology, but we know that it's there, and we know that it's having a profound effect on the fate of the universe. Think about it. The universe is not just expanding, it's expanding faster and faster. This accelerated expansion is being driven by dark energy, and it's changing the way we think about the future of the cosmos. In the next chapter, we'll dive deeper into the mysteries of dark energy and explore its implications for the ultimate fate of the universe. Will the universe continue to expand forever, eventually becoming a cold, dark, and empty place? Or will dark energy eventually weaken, causing the expansion to slow down and perhaps even reverse? These are the questions that cosmologists are grappling with today, and while we don't have all the answers yet, the quest to understand the universe is one of the most exciting and rewarding endeavors in science. And as always, I want to hear from you. Where are you watching from today? What are your thoughts on the infinite universe? Let me know in the comments below. I love hearing from fellow space enthusiasts around the world. Until next time, keep looking up. Okay, so we've established that the observable universe, that bubble of space we can actually see, is a whopping 93 billion light years across. Imagine that number scrawled across the cosmos, each digit a galaxy unto itself. 93 billion light years. The light you're seeing from the furthest reaches of that bubble started its journey billions of years ago, before humans even walked the Earth. And beyond that, potentially more universe stretching on forever, maybe even an infinite universe swirling with nebulae painted across an endless canvas. Think about that for a moment. Infinity. It's a concept that's easy to say, a word that rolls off the tongue with deceptive ease, but almost impossible to truly grasp. It's like trying to hold the ocean in your hands. You can describe it, you can feel it spray, but you can never truly contain it. I remember staring up at the night sky as a kid, trying to imagine where it all ended. The sheer, overwhelming vastness would send shivers down my spine, a mixture of awe and a profound sense of insignificance. Infinity is like that feeling, amplified to a cosmic scale. But even if the universe is infinite, a boundless ocean of stars and galaxies, there's another mind-bending possibility we need to consider. Multiple universes. Are we alone in this cosmic arena, the sole players in this grand cosmic drama? Or are there other universes out there, perhaps with different laws of physics, different constants, different everything? Universes where gravity is weaker, where light travels slower, where perhaps even time itself flows differently. This is where we delve into the fascinating and highly speculative realm of the multiverse. Now, before your head explodes, and trust me, I understand the feeling, let's break down some of the ideas behind the multiverse. It's not just one single theory, a neat, easily digestible package of concepts, but rather a collection of hypotheses, each with its own implications and potential mechanisms. It's a landscape of possibilities, some more plausible than others, all vying for attention in the arena of theoretical physics. It's a bit like exploring a jungle. You might find incredible treasures, but you also might stumble into a swamp of dead ends. One of the most popular ideas stems from inflation, the period of incredibly rapid expansion that the universe underwent in its earliest moments. Remember how we talked about the Big Bang, that singularity from which everything sprang forth, and the cosmic microwave background, the afterglow of that event? Well, inflation happened before that, within the first fraction of a second after the universe began. An unfathomably short amount of time, yet it shaped everything that followed. We believe it expanded faster than the speed of light, a concept that seems to defy everything we know about physics. Think of it like this. Imagine blowing up a balloon. Initially, the balloon expands slowly and relatively uniformly. You can see the surface stretch and grow, a smooth, even expansion. But then, imagine a tiny patch on the balloon suddenly starting to inflate much faster than the rest. A localized explosion of expansion, a bulge forming with incredible speed. That's kind of like inflation. It's not a perfect analogy, of course, but it helps to visualize the sheer scale and speed of what we're talking about. The theory of eternal inflation suggests that this rapid expansion isn't just a one-time event, a singular burst that happened in the distant past. Instead, it's an ongoing process, a constant bubbling and churning at the edges of reality. While our universe settled down after its initial inflationary burst, cooling and forming galaxies and stars, other regions of space might still be undergoing inflation, creating bubble universes that are constantly popping into existence, like bubbles in a cosmic champagne. These are often referred to as Level 1 multiverse. These bubble universes could have vastly different properties from our own. The fundamental constants of nature, like the strength of gravity, the electromagnetic force, or the mass of the electron, which seem so finely tuned to allow for life as we know it, might be completely different in other universes. Imagine a universe where gravity is so strong that stars collapse into black holes almost immediately, or one where the electromagnetic force is so weak that atoms can't even form. Some might be devoid of matter, a vast emptiness stretching on forever. Some might collapse in on themselves immediately, crushed by their own gravity. And some might be governed by physical laws we can't even imagine, laws that would make our current understanding of the universe seem like child's play. So what does this mean for the size of the universe, or rather, the multiverse. Well, if eternal inflation is correct, the multiverse could be unimaginably vast, potentially infinite. Each bubble universe would be like its own separate cosmos, disconnected from all the others, floating in an endless sea of expanding space. It's a truly mind-boggling concept, one that challenges our very notion of reality. Another intriguing idea comes from quantum mechanics, the branch of physics that governs the behavior of matter at the atomic and subatomic level. This is where things get really weird. One of the most bizarre concepts in quantum mechanics is the idea of superposition, where a particle can exist in multiple states at the same time until it is measured. It's like the particle can't make up its mind, existing in a hazy, uncertain state until we force it to choose. Think of Schrödinger's cat, a famous thought experiment designed to illustrate the strangeness of quantum mechanics. The cat is placed in a box with a vial of poison that might or might not be released, depending on the decay of a radioactive atom. According to quantum mechanics, until we open the box and observe the cat, it's in a superposition of being both alive and dead simultaneously. It's not that we don't know if it's alive or dead, it's that according to the theory, it is both alive and dead, in a probabilistic blur of possibilities. The many worlds interpretation of quantum mechanics takes this idea to its logical extreme. It suggests that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different possible outcome. Every time a quantum event occurs, the universe forks, creating a new branch of reality. This is often referred to as level 3 multiverse. So in one universe, Schrödinger's cat is alive, purring contentedly, and in another, it's dead, a victim of quantum randomness. And this happens for every quantum event, all the time. Every electron that passes through a slit, every atom that decays, every interaction between particles creates a new universe. The number of universes branching off every second would be astronomical, beyond our ability to comprehend, a number so large it would make even the most seasoned mathematician's head spin. If the many worlds interpretation is correct, then the multiverse isn't just a collection of disconnected bubble universes, like islands in a vast ocean, but rather a vast branching tree of possibilities with every decision, every quantum event creating new realities. It's a constantly evolving, ever-expanding web of universes, each slightly different from the others, each reflecting a different possible outcome of the quantum dice roll. How big would that multiverse be? Again, potentially infinite. Every possible scenario, every possible choice played out in its own separate universe. A universe where you decided to take that different job, a universe where you met a different person, a universe where you made a different choice at every single moment of your life. It's a mind-boggling concept, isn't it? It suggests that every regret, every missed opportunity exists in another universe, a constant reminder of the paths not taken. Now I know what you might be thinking, this all sounds like science fiction, and you wouldn't be entirely wrong. The multiverse is still largely theoretical, a playground for physicists and cosmologists to explore the boundaries of our knowledge. There's no direct observational evidence to support its existence, yet no telescope powerful enough to peer into another universe. But that doesn't mean it's not worth exploring. Science is, at its heart, about asking questions and pushing the boundaries of what we know. Scientists are actively searching for evidence that could hint at the existence of other universes. One possibility is to look for collisions between our bubble universe and another one. Such a collision could leave a subtle imprint on the cosmic microwave background, a circular pattern of slightly different temperatures, a cosmic scar from a long-ago encounter. It would be like finding a fingerprint on the fabric of space-time. Another approach is to look for evidence of extra dimensions. String theory, a theoretical framework that attempts to unify all the fundamental forces of nature, suggests that the universe has more than the three spatial dimensions, length, width, and height, that we experience. These extra dimensions are thought to be curled up at incredibly small scales, far beyond our ability to directly observe them, but they could still have subtle effects on the behavior of particles and gravity. This is often referred to as Level 2 multiverse. Finding evidence for extra dimensions wouldn't directly prove the existence of a multiverse, but it would lend support to the theoretical frameworks that predict it. It would be like finding a piece of a puzzle that fits into a larger picture, a piece that suggests there's more to the universe than meets the eye. So where does all of this leave us in our quest to understand the size of the universe? Well, the answer is complicated. If our universe is just one of many in a vast multiverse, then the concept of size becomes almost meaningless. How do you measure the size of something that might be infinite, or that might contain an infinite number of other universes? It's like trying to measure the length of a dream. Perhaps the question isn't so much about the size of the universe or multiverse, but about its nature. What are the fundamental laws of physics that govern its behavior? What are the possibilities that are allowed within its framework? What are the limits of reality itself? These are questions that scientists are still grappling with, and the answers may be even more mind-bending than we can currently imagine. The search for understanding the universe and the multiverse is an ongoing journey full of twists and turns, surprises and uncertainties. It's a journey that may never truly end, a quest for knowledge that will continue to push the boundaries of human understanding. And that's what makes it so exciting. The unknown, the potential for discovery, the sheer audacity of trying to understand something so vast and complex. It's a testament to the human spirit, our insatiable curiosity, our unwavering desire to explore the universe and our place within it. But let's bring it back to something a little more concrete, something we can potentially observe. We've talked about the observable universe, the CMB, and even the possibility of detecting collisions with other bubble universes. But what about the ultimate fate of our own universe? Will it expand forever, growing colder and emptier with each passing eon, or will it eventually collapse back in on itself, crushed by its own gravity in a big crunch? The answer, it turns out, depends on a mysterious force that we still don't fully understand, dark energy. And that's what we'll discuss next. Okay, so we've danced around the edges of it, haven't we? This thing that dominates our universe, this invisible hand shaping its destiny. Dark energy. We've mentioned it. We've even quantified it, 68% of everything. But what is it? And perhaps more importantly, what does it mean for the long, long, long game? That's where we're headed now. Let's get one thing straight. We don't know what dark energy is. If we did, I wouldn't be using phrases like invisible hand and thing. I'd be rattling off equations and explaining its quantum properties, but we can describe its effects with reasonable certainty. Think of it like this. You might not know exactly how your car engine works, but you know that when you turn the key, it usually makes the car go. We see the universe expanding, and not just expanding, but accelerating. Something is pushing it outwards, fighting against gravity's relentless pull. That something is what we call dark energy. Now, you might be thinking, okay, so it's a force, like gravity, or electromagnetism. Not exactly. It doesn't seem to act like any force we're familiar with. Gravity pulls things together. Electromagnetism can both attract and repel, depending on the charges. Dark energy, as far as we can tell, only repels, and it does so uniformly across the entire universe. One of the leading theories about dark energy is that it's a property of space itself. Yes, you read that right. Space itself might have an inherent energy density. Think about that for a moment. Empty space, the void, the nothingness between stars and galaxies isn't truly empty. It's bubbling with a mysterious energy that's causing the universe to inflate like a cosmic balloon. This idea isn't as crazy as it sounds. Quantum field theory, which is one of the most successful theories in physics, predicts that even in a perfect vacuum, there's a certain amount of energy present, called the vacuum energy. This energy arises from the constant creation and annihilation of virtual particles that pop into existence for a fleeting moment before disappearing again. It's a bizarre, almost magical concept, but it's supported by experimental evidence. The problem? The amount of vacuum energy predicted by quantum field theory is vastly, vastly larger than what we observe as dark energy. Like 120 orders of magnitude larger. That's a 1 followed by 120 zeros. It's one of the biggest discrepancies in all of physics. So either our understanding of quantum field theory is incomplete, likely, or there's some other mechanism at play that's cancelling out most of the vacuum energy, leaving only a tiny amount to act as dark energy. Or perhaps dark energy isn't vacuum energy at all, but something else entirely. Another possibility is that dark energy is a new kind of fundamental field, similar to the Higgs field that gives particles mass. This hypothetical field, sometimes called quintessence, would permeate the universe and exert a repulsive force. Unlike the vacuum energy, which is constant, the strength of quintessence could change over time. This would make the universe's expansion rate dynamic and unpredictable. Think about it. If dark energy is quintessence, its density could increase over time, leading to an even faster expansion. Or it could decrease, eventually allowing gravity to regain control and reverse the expansion. The possibilities are, well, they're cosmic. Regardless of what dark energy actually is, its effects are undeniable. The universe is expanding, and it's expanding faster and faster. This has profound implications for the future. Let's play out a few scenarios, shall we? These are, of course, based on our current limited understanding, and things could change dramatically as we learn more. But it's fun and a little terrifying to speculate. Scenario 1, the Big Rip. This is the most dramatic and arguably the most unsettling outcome. If dark energy continues to increase in strength, the expansion of the universe will accelerate without bound. Eventually, the repulsive force of dark energy will become so strong that it overcomes all other forces, including gravity, electromagnetism, and even the strong and weak nuclear forces that hold atoms together. Imagine this. First, galaxies would be torn apart. Then solar systems would disintegrate. Planets would be ripped from their stars. And finally, even atoms themselves would be pulled apart, leaving behind a sea of elementary particles flying away from each other at ever-increasing speeds. The universe would literally be ripped apart at its seams. It's a rather unpleasant thought, isn't it? The good news, if you can call it that, is that the Big Rip is thought to be the least likely scenario, but it's still on the table. Scenario 2, the heat death. Big freeze. This is the most widely accepted scenario, and it's a bit less dramatic, though still pretty bleak. If dark energy remains constant, as current observations suggest, the universe will continue to expand at an accelerating rate. Galaxies will move further and further apart, eventually becoming so distant that they'll be invisible to each other. Stars will eventually burn out, one by one. New stars will cease to form as the gas and dust needed to create them become too diffuse. Black holes will eventually evaporate through Hawking radiation, a process that takes an incredibly long time, mind you. The universe will become increasingly cold, dark, and empty. Eventually, it will reach a state of maximum entropy, where there's no more usable energy and no more activity. It's a slow, agonizing fade into oblivion. Think of it as the ultimate cosmic entropy. This scenario is often called the heat death, because the universe will eventually reach a state of thermal equilibrium, where everything is at the same temperature and there's no more energy available to do work. It's a rather depressing thought, isn't it? But hey, at least we won't be ripped apart. Scenario 3, the big crunch, a possible comeback. This scenario is becoming less likely as we gather more data about dark energy, but it's still worth considering. If dark energy were to weaken over time, gravity could eventually regain control and begin to pull the universe back together. The expansion would slow down, stop, and then reverse. Galaxies would start to move towards each other. The universe would become increasingly hot and dense. Eventually, everything would collapse into a single point, a singularity. This is the reverse of the Big Bang, and it's often called the Big Crunch. Some physicists speculate that the Big Crunch could lead to another Big Bang, creating a cyclical universe that expands and contracts endlessly. It's a neat idea, but there's no evidence to support it. And, given what we know about dark energy, it seems increasingly unlikely. But who knows? The universe is full of surprises. Scenario 4, something else entirely. This is the most likely scenario of all, in my opinion. We simply don't know enough about dark energy to predict the future with any certainty. There could be unforeseen factors, new discoveries, or entirely new physics that we haven't even considered yet. Maybe dark energy will change its behavior in unexpected ways. Maybe there's a connection between dark energy and dark matter that we don't understand. Maybe there's a fifth force of nature that's influencing the expansion of the universe. The possibilities are endless, and that's what makes science so exciting. So what's the takeaway from all of this? Dark energy is a mystery, a big universe-sized mystery. It dominates the cosmos, shapes its destiny, and yet we have no idea what it actually is. But that doesn't mean we should give up trying to figure it out. On the contrary, it means we should double down on our efforts. We need to build better telescopes, conduct more sophisticated experiments, and develop new theoretical models. The fate of the universe may depend on it. Okay, let's dive deeper into the cosmic ocean. So here we are, contemplating the potential end of everything, or at least everything we know. The big rip, the heat death, maybe even a big crunch. These are the headline-grabbing finales. But what if I told you there's another, perhaps even stranger possibility lurking in the wings? What if instead of a dramatic universe-spanning event, our cosmos simply fades away? Think about that for a moment. We've spent a lot of time discussing the expansion of the universe, driven by the relentless push of dark energy. Now remember that dark energy isn't something we fully understand. Understatement of the century, right? We have theories like vacuum energy and quintessence, but the truth is, its nature is still a profound mystery. And this mystery is crucial because it dictates not just the rate of expansion, but potentially the very fabric of space-time itself. Now let's introduce a concept that might sound like science fiction, and let's be honest, it is pretty speculative. False vacuum decay. What's a vacuum, you ask? Good question. In physics, the vacuum isn't just empty space, it's the lowest energy state of a particular region. Imagine a ball at the bottom of a valley. That's its lowest energy state, its true vacuum. Now imagine a tiny dimple on the side of that valley. The ball could sit there seemingly stable, but it's not at the absolute bottom. It's in a false vacuum. It looks stable, but it's actually primed for change. Our universe, according to some theories, might be in just such a false vacuum state. What does this mean? Well, imagine a quantum event, a tiny random fluctuation that causes our universe to tunnel to a lower energy state, a true vacuum. Quantum tunneling, for those who need a refresher, is the ability of a particle to pass through a barrier, even if it doesn't have enough energy to overcome it classically. Think of it like a ghost walking through a wall. This tunneling event would create a bubble of true vacuum. And here's the kicker. This bubble would expand, not just expand, but expand at the speed of light. Think about that for a moment. A bubble of altered physics, racing outwards, rewriting the laws of nature as it goes. What would happen inside this bubble? That's where things get complicated. The laws of physics, as we know them, might cease to exist. The fundamental constants, the speed of light, the gravitational constant, the masses of elementary particles, could all be different. Atoms might not be stable. Matter, as we understand it, might simply dissolve. Essentially, everything inside the bubble would be converted into something else, something governed by a different set of rules. Now I know what you're thinking. That sounds terrifying, and, well, it is a pretty unsettling prospect. But before you start building your doomsday bunker, let's put this into perspective. First, the probability of false vacuum decay happening at all is extremely low. We're talking about quantum events at the most fundamental level of reality. It's like waiting for a single atom in your body to spontaneously teleport to the moon. Possible, yes. Likely, absolutely not. Second, even if a bubble of true vacuum did form, it would likely be somewhere incredibly far away, in the vast emptiness of intergalactic space. The chances of it forming right here, right now, are astronomically small. Third, and perhaps most importantly, we wouldn't see it coming. The bubble expands at the speed of light, meaning there would be no warning. One moment, everything is normal. The next, well, there is no next. So why even talk about it? Because it highlights just how much we don't know about the universe. It reminds us that our current understanding of physics is, at best, incomplete, and it's a mind-blowing example of the kind of existential threats that could, however unlikely, be lurking out there. It also ties back into the multiverse concept we discussed earlier. If false vacuum decay is possible, and if it can create regions with different physical laws, then it's entirely conceivable that other universes are constantly being born from these events. Our universe could be just one bubble in an endless sea of bubbles, each with its own unique set of physical constants. Think about that for a moment. The implications are staggering. It means that the laws of physics that govern our reality are not necessarily universal. They're just the rules of our particular game. Other universes might have different rules, different constants, different possibilities. This brings us back to the question of fine-tuning. Why are the physical constants in our universe so precisely tuned for life? If they were even slightly different, stars wouldn't form, atoms wouldn't be stable, and life as we know it wouldn't be possible. One answer, of course, is that we simply got lucky. We happen to live in a universe with the right conditions for life. But the multiverse offers another, more intriguing explanation, that there are countless universes, each with different physical constants. In most of these universes, life is impossible, but in a few like ours, the conditions are just right. And naturally, we find ourselves in one of those universes. It's a form of selection bias, sometimes called the anthropic principle. We can only observe universes that allow for observers to exist. It's a controversial idea, to be sure. Science loves a good debate. but it's one that continues to fascinate physicists and cosmologists. Now let's shift gears slightly. We've talked about the potential end of the universe, the possibility of false vacuum decay, and the mind-bending concept of the multiverse. But what about something a little more tangible, something we can actually see? Let's talk about galaxies. We live in the Milky Way galaxy, a spiral galaxy containing hundreds of billions of stars. But the Milky Way isn't alone. It's part of a local group of galaxies, which in turn is part of a larger supercluster called Laniakea. Yes, astronomers have a knack for giving things cool names. These galaxies are gravitationally bound to each other. They're constantly interacting, merging and colliding. And in the distant future, the Milky Way is destined for a head-on collision with its nearest major neighbour, the Andromeda Galaxy. This collision, predicted to occur in about 4.5 billion years, sounds catastrophic. Hollywood, are you listening? But in reality, it's likely to be a much more gradual and less destructive process than you might imagine. Think about it. Galaxies are mostly empty space. The stars within them are incredibly far apart. When two galaxies collide, it's more like two swarms of bees passing through each other than two billiard balls smashing together. There will be some gravitational disruption, of course. Stars will be flung into new orbits. Gas and dust clouds will collide and compress, triggering bursts of star formation. But the vast majority of stars will survive the encounter. Over billions of years, the Milky Way and Andromeda will gradually merge into a single larger galaxy. This new galaxy, sometimes nicknamed Milkomeda, will be an elliptical galaxy, a giant ball of stars formed from the merger of two spirals. Think about that for a moment. Our familiar Milky Way transformed into something entirely new. It's a reminder that the universe is constantly evolving, constantly changing, and that even the most seemingly stable structures are ultimately temporary. So where does this leave us? We've journeyed from the observable universe to the multiverse, from the Big Bang to the potential Big Rip, or heat death, or false vacuum decay. We've explored dark energy, dark matter, and the fate of the cosmos. We've contemplated the infinite and the infinitesimal, and hopefully, we've gained a deeper appreciation for the sheer scale, complexity, and mystery of the universe. But remember, this is just the beginning. There's still so much we don't know, so many questions unanswered, and that's what makes cosmology so exciting. It's a field of constant discovery, of pushing the boundaries of human knowledge, and who knows? Maybe one day, you will be the one to unravel the secrets of the universe. Okay, so we've talked about the observable universe, its contents, and even a cosmic collision in our future. But something's been lurking in the background, a shadowy presence that's pulling the strings of the cosmos itself. I'm talking, of course, about dark energy. Now I know what you might be thinking. Dark energy sounds like something out of a science fiction movie. And you wouldn't be entirely wrong, it is pretty wild stuff. But it's also one of the most important and baffling discoveries in modern cosmology. It's so important, in fact, that understanding it is key to understanding the ultimate fate of the universe. Think about that for a moment. The fate of everything hinges on this dark energy. So what exactly is dark energy? That, my friend, is the million-dollar question, or rather the trillion-dollar, or maybe even the entire budget of the universe dollar question. If there was a budget, that is. We don't really know, but we know it's there, we see its effects. It's like knowing there's a ghost in your house because the doors keep slamming shut even though you can't see the ghost itself. Here's how we discovered it. For decades, astronomers had been carefully measuring the expansion rate of the universe. They knew it was expanding. Edwin Hubble figured that out back in the 1920s, remember him? But the expectation was that the expansion should be slowing down over time due to the gravitational pull of all the matter in the universe. Makes sense, right? Gravity pulls things together, expansion pushes them apart. It's a cosmic tug of war. Then in the late 90s, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, made a groundbreaking discovery. They were studying distant supernovae, exploding stars, using them as standard candles to measure cosmic distances. What they found was astonishing. The expansion of the universe wasn't slowing down, it was speeding up. Imagine throwing a ball up in the air, and instead of slowing down and falling back to Earth, it starts accelerating upwards, faster and faster. That's essentially what the universe is doing. This acceleration implied the existence of some mysterious force counteracting gravity on the largest scales. And that force, whatever it was, became known as dark energy. 'Cause, well, we didn't know what else to call it. And mysterious force counteracting gravity is a bit of a mouthful. The immediate question, of course, was where is it coming from? That's where things get really interesting and really speculative. The leading theory is that dark energy is a property of space itself. Think about that for a moment. Space itself has energy. According to quantum mechanics, the theory that governs the behavior of matter at the subatomic level, even seemingly empty space is not truly empty. It's filled with virtual particles that are constantly popping in and out of existence. These particles, though fleeting, contribute to the overall energy density of space. This energy is often referred to as vacuum energy or zero-point energy. Now here's the rub. When physicists try to calculate the amount of vacuum energy that should be present in the universe, they came up with a number that was vastly, ridiculously, astronomically larger than what we actually observe. By a factor of something like 1 in 220. That's a 1 followed by 120 zeros. To put that in perspective, that's like saying you have $1, but you should have enough money to buy every single atom in the observable universe 1,000,000 times over. It's a huge discrepancy, and it's one of the biggest unsolved problems in physics. Why is the observed amount of dark energy so small compared to what theory predicts? We don't know. It's a major embarrassment for theoretical physicists. Another possibility is that dark energy isn't constant but changes over time. This idea is often referred to as quintessence. Sounds cool, doesn't it? Like something out of ancient alchemy. Quintessence is a hypothetical dynamic energy field that permeates space. Unlike the cosmological constant, which is constant, the density of quintessence can vary over time and space. Imagine dark energy as a dial that someone is slowly turning up or down. If it's being turned up, the expansion of the universe will accelerate even faster. If it's being turned down, the expansion might slow down or even reverse. The problem is, we haven't detected any evidence of quintessence. It's just an idea, a possibility, a way to try to extol the accelerated expansion without resorting to a cosmological constant. So, but what does all this mean for the future of the universe? Well, the fate of the universe is inextricably linked to the nature of dark energy. Remember those potential fates we talked about? The Big Rip, heat death, Big Crunch, and false vacuum decay. Dark energy plays a starring role in most of them. If dark energy is indeed a cosmological constant and its density remains constant over time, then the universe will likely continue to expand forever, at an ever-increasing rate. This scenario leads to the heat death of the universe. Galaxies will drift further and further apart, stars will eventually burn out, and the universe will become cold, dark, and empty. Think of it as the ultimate cosmic burnout. But what if dark energy isn't constant? What if its quintessence and its density increases over time? In that case, we could be headed for the Big Rip. As dark energy becomes stronger and stronger, it will eventually overcome all other forces in the universe, including gravity, electromagnetism, and the strong and weak nuclear forces. Galaxies will be torn apart, then solar systems, then planets, and ultimately even atoms themselves. The universe will be ripped apart at its seams. Not a pleasant thought, is it? On the other hand, if dark energy somehow weakens over time, the expansion of the universe could slow down and eventually reverse. Gravity would then take over, pulling everything back together in a big crunch. The universe would collapse in on itself, becoming hotter and denser until it reaches a singularity, the opposite of the Big Bang. Now, the Big Crunch scenario seems less likely given current observations. All the data points to a universe that is continuing to expand at an accelerating rate. But hey, you never know. The universe is full of surprises. And then there's the wild card, false vacuum decay. Remember that one? It's a quantum event that could, theoretically, create a bubble of true vacuum that expands at the speed of light, altering the laws of physics within. If that happens, well, it wouldn't matter what dark energy is doing. Everything would be rewritten anyway. So, where does that leave us? We're left with a universe that is expanding at an accelerating rate, driven by a mysterious force called dark energy. We don't know what dark energy is, but we have some ideas, and the fate of the universe hinges on which of those ideas is correct. It's a bit daunting, isn't it? But also incredibly exciting. We're living in a time when we can ask these fundamental questions about the universe and try to answer them using science. We may not have all the answers yet, but we're making progress. And who knows, maybe someday you, the reader, will be the one to solve the mystery of dark energy. Now, you might be asking, okay, that's all fascinating, but what can I do about it? Well, you can start by staying curious. Keep asking questions, keep learning, and support scientific research. Because the more we know about the universe, the better equipped we'll be to understand our place in it, and to prepare for whatever the future may hold, even if that future involves a big rip, a heat death, or something even stranger. And perhaps more practically, keep an eye on the news. Scientists are constantly gathering more data and refining their theories about dark energy. New discoveries could change everything we think we know about the universe. Next time, we'll delve into the mind-bending concept of extra dimensions. Get ready to think outside the box, or, well, outside the 3 dimensions we're used to. Okay, let's dive into Chapter 8 and explore the mind-bending world of extra dimensions. So we've danced on the edge of the observable universe, peered into the ancient light of the Big Bang, and even flirted with the idea of countless other universes. Remember that feeling standing on the precipice of infinity? The wind whipping past as you stared into the cosmic abyss. Good. Because what if I told you that the universe might be even stranger than all that? What if the 3 dimensions we experience, length, width, and height, aren't the only ones out there? I can practically hear the collective groan. More mind-blowing stuff? Seriously? But trust me, this is worth it. This is the kind of stuff that keeps physicists up at night, fueled by lukewarm coffee and the burning desire to understand the very fabric of reality. I know, it sounds like something straight out of a science fiction movie. Images of wormholes shimmering in space, fantastical creatures flitting between realities, and intrepid explorers venturing into the unknown probably spring to mind. But the concept of extra dimensions isn't just a playground for imaginative writers. It's a serious topic of investigation in theoretical physics, particularly in string theory and M-theory. It's a mathematical framework painstakingly constructed that suggests these extra dimensions might be real, might be vital. Before we get too far ahead of ourselves, let's make sure we're all on the same page. What is a dimension anyway? It's easy to throw the word around, but what does it actually mean? We tend to think of them as directions in which we can move. You can walk forward, length, sideways, width, or jump up, height. Those are the three spatial dimensions we're intimately familiar with. We navigate them every single day, rarely giving it a second thought. And then there's time, often considered the fourth dimension, which dictates our position in space-time. It's the relentless river that carries us from birth to death, from one moment to the next. But what if there were more? More directions to travel, more axes to exist upon? The thought alone makes my head spin a little. Think about this for a moment. Imagine you're an ant crawling on a clothesline. Picture that tiny creature, its minuscule legs gripping the rough fibres of the rope. To you, the clothesline is essentially a one-dimensional object. You can only move forward or backward. You have no concept of up or down relative to the clothesline. Your entire universe is confined to that single line. Now, imagine a human looking at that same clothesline. We see the ant, but we also see the clothesline's thickness, a second dimension that the ant can't perceive. We can reach down and pluck the ant off the line, moving it in a direction it can't even comprehend. The ant is trapped in its one-dimensional world, completely oblivious to the extra dimension that's right there surrounding it. Could we be like that ant, stuck in our three-dimensional world, unaware of other dimensions that are all around us? Could we be blindly navigating a universe that's far more complex and intricate than we can possibly imagine? That's the mind-blowing possibility that physicists are exploring. I remember the first time I truly considered this. I was a grad student crammed into a tiny office overflowing with textbooks and research papers. The late-night coffee wasn't helping. My eyes were burning and my brain felt like it was about to short-circuit. But then, as I wrestled with the equations of string theory, it hit me. We might be missing something fundamental, something huge. The feeling was a mixture of terror and exhilaration. And the reason they're exploring it isn't just out of sheer curiosity, though that's definitely a factor. Scientists at their core are driven by an insatiable desire to understand. It's because extra dimensions might help us solve some of the biggest mysteries in physics, like the nature of gravity and the unification of all the fundamental forces. Let's unpack that a bit. One of the biggest challenges in physics is reconciling general relativity, Einstein's theory of gravity, which describes the universe on a large scale, with quantum mechanics, which describes the universe on a very small scale. It's like trying to fit two pieces of a puzzle together when they are from entirely different sets. The two theories work incredibly well in their respective domains, but they clash when you try to apply them to the situations where both gravity and quantum effects are strong, like inside a black hole or at the very moment of the Big Bang. These are the places where our understanding of the universe breaks down, where the laws of physics as we know them simply cease to apply. String theory and its more advanced cousin M theory propose that the fundamental building blocks of the universe aren't point-like particles but tiny vibrating strings. Imagine the strings on a violin, each vibrating at a different frequency to produce a different note. In string theory, these strings vibrate in different ways to create all the particles and forces we observe. And these strings don't just exist in 3 spatial dimensions, they require 10 dimensions, or 11 in M theory to be mathematically consistent. The equations simply don't work without them. Where are these extra dimensions then? If they're all around us, why can't we see them? Are we simply blind to their existence like the ant on the clothesline? Well, one possibility is that they're compactified, which is a fancy way of saying they're curled up into incredibly tiny sizes, far too small for us to detect a rare solar. Think of a garden hose. From a distance it looks like a one-dimensional line, but if you get closer, you'll see that it also has a circular dimension around its circumference. You can walk around the hose, tracing that circle. That circular dimension is compactified, it's there, but it's much smaller than the length of the hose. The extra dimensions in string theory could be curled up in a similar way, perhaps at the Planck scale, around 10 to 35 meters, which is far, far smaller than anything we can currently probe with our most powerful microscopes. It's a scale so unimaginably small that it's almost impossible to grasp. To put it in perspective, if an atom were the size of the solar system, the Planck scale would be roughly the size of a virus. Another possibility is that we are confined to a three-dimensional brain, short for membrane, within a higher dimensional space. Imagine a thin sheet floating in a room. You can move around on the sheet, but you can't easily move off of it into the rest of the room. We could be living on such a brain, trapped in our three-dimensional existence with the other dimensions existing all around us, just out of reach. In this scenario, gravity might be the only force that can leak into the extra dimensions, which could explain why it's so much weaker than the other fundamental forces, like electromagnetism and the strong and weak nuclear forces. Think about that for a moment. Gravity is what holds planets in orbit around stars, and stars in orbit around the centers of galaxies. It's the force that governs the large-scale structure of the universe. It's the reason we're all stuck to the Earth and not floating off into space. And yet it's incredibly weak compared to the force that holds atoms together. A simple refrigerator magnet can overcome the entire gravitational pull of the Earth to hold itself against the fridge door. It's a cosmic imbalance that has puzzled physicists for decades. If gravity is leaking into extra dimensions, that could explain why it seems so feeble to us. It's like its strength is being diluted across a larger volume of space. Imagine pouring a glass of water into a swimming pool. The water is still there, but it's so dispersed that it's practically undetectable. Now, I know this all sounds incredibly abstract and theoretical, and it is, but physicists are actively searching for evidence of extra dimensions. This isn't just in-will speculation, it's a serious scientific endeavour. One way they're doing this is by looking for subtle deviations from the laws of gravity at very small distances. If gravity is indeed leaking into extra dimensions, it might behave slightly differently than we expect at these scales. They are conducting incredibly precise experiments, pushing the limits of our technology to try and detect these tiny variations. Another approach is to look for miniature black holes. String theory predicts that if extra dimensions exist, it might be possible to create tiny black holes in high-energy particle collisions at the Large Hadron Collider, LHC, at CERN. These black holes would be incredibly small and short-lived, popping into existence and then almost immediately decaying. But their decay products could provide telltale signs of their existence and the presence of extra dimensions. They would leave behind a unique signature, a pattern of particles that could only be explained by the presence of these miniature black holes. So far, no evidence of extra dimensions has been found at the LHC, but the search continues. Scientists are constantly analysing the data, refining their models, and pushing the LHC to its limits. And even if we don't find direct evidence of extra dimensions, the very fact that we're exploring these ideas is pushing the boundaries of our understanding of the universe. It's forcing us to think in new ways, to challenge our assumptions, and to develop new tools and techniques. The concept of extra dimensions also raises some profound philosophical questions. If there are more dimensions than we can perceive, what else might we be missing? What other aspects of reality are hidden from our senses? Are there entire universes existing right alongside ours, completely invisible to us? It's a humbling thought, isn't it? We tend to think of ourselves as having a pretty good grasp of how the universe works. We've mapped the cosmos, deciphered the genetic code, and split the atom. But the possibility of extra dimensions reminds us that there's always more to discover, more to explore, and more to wonder about. The universe is infinitely complex, and our understanding of it is constantly evolving, and that's what makes science so exciting. The universe is full of surprises, and the more we learn, the more we realize how much we don't know. The journey of discovery is never truly over. It's a never-ending quest, driven by curiosity and the desire to understand the fundamental nature of reality. So where do we go from here? Well, in the next chapter, let's explore one of the most bizarre and unsettling predictions of modern cosmology, the possibility that our universe isn't alone, and that it might one day collide with another universe. Buckle up, because things are about to get really weird, and please leave your comments down below. I want to know what you think about extra dimensions. Are you convinced? Skeptical? Completely baffled? Let's talk about it. What's the most bizarre implication you can imagine if extra dimensions are real? Let me know. Okay, so where were we? Ah yes, extra dimensions. A mischievous glint sparked in my eye as I remembered the mental gymnastics required to even begin grasping the concept. Now, I know what you might be thinking, I said, leaning forward conspiratorially. Extra dimensions. Sounds like science fiction. And you wouldn't be entirely wrong. It does sound like something straight out of a space opera. Think of hyperspace jumps, or entire civilizations living in pocket universes. The stuff of dreams, right? I paused, letting the image sink in. But the truth is, I continued, lowering my voice slightly, the idea of extra dimensions is a serious topic in theoretical physics, and it could potentially hold the key to some of the biggest mysteries in the universe. I ran a hand through my hair, a nervous habit that always surfaced when discussing truly profound ideas. Think about that for a moment. The very fabric of reality, possibly woven with threads we can't even directly perceive. I imagined the universe not as a simple three-dimensional stage, but as a complex tapestry, its intricate details hidden from our limited senses. So, what exactly are extra dimensions? I asked, raising an eyebrow. Well, we're all familiar with the three spatial dimensions: length, width, and height. We move through them every day. We can go forward, backward, left, right, up and down. Simple, right? I snapped my fingers for emphasis. Then there's time, which Einstein showed is intertwined with space to create space-time. But what if there were more? I let the question hang in the air, a pregnant pause filled with unspoken possibilities. What if there were dimensions curled up so small that we can't see them? I shifted my weight, trying to find the right analogy. Imagine a tightrope walker. I began, picturing a lone figure silhouetted against the sky. To them, the rope is essentially one-dimensional near. They can only move forward or backward. Their world is a linear path, a constant balancing act. I paused, letting the image solidify. But to a tiny ant crawling on that same rope, there's another dimension, the circumference of the rope. It can crawl around the rope, exploring a hidden world that the tightrope walker is completely oblivious to. It can experience a freedom of movement the walker doesn't even know exists. I smiled, pleased with the analogy. Now scale that up, way, way up, and you get the idea of how extra dimensions might work. They could be curled up at the Planck scale, that's about 1.6 + 10 to 35 meters, incredibly tiny. So small that we haven't been able to detect them directly. I shuddered, imagining the sheer tininess of it all. It was mind-boggling. I could almost hear the skeptical voices in my head. But why? They would ask. Why would physicists even consider such a wild idea? I anticipated the question with a sigh. Well, one of the biggest motivations comes from string theory. String theory attempts to unify all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force and the weak nuclear force, into a single elegant framework. It's the holy grail of physics, the theory of everything. I emphasized the last phrase with a flourish. And guess what? String theory requires extra dimensions to work mathematically. It's not just a nice to have, it's essential. I paused, letting the weight of that statement sink in. In fact, I continued, most versions of string theory need 10 dimensions in total, 9 spatial and 1 time, while some versions, like in theory, require 11. I threw my hands up in mock exasperation. 11 dimensions! It sounds absurd, doesn't it? But the math doesn't lie. The equations demand it. I leaned forward, lowering my voice again. Think about that for a second. Our entire universe, everything we see and experience, could be just a tiny slice of a much larger, multi-dimensional reality. I imagined our three-dimensional world as a thin film floating in a vast ocean of unseen dimensions. But hold on, I said, raising a hand to forestall any objections. I know what you're thinking. If these extra dimensions exist, why don't we see them? Why aren't we bumping into things in the 5th dimension? I chuckled. That's where the concept of compactification comes in. The idea is that these extra dimensions are curled up into tiny, complex shapes, like the Calabi-Yau manifolds, which are far too small for us to detect direct, or they're hidden, tucked away in the fabric of space-time. I pictured these manifolds as intricate, microscopic origami, folded and twisted into impossible shapes. It's like the ant on the tightrope. The extra dimension is there, but it's not readily apparent to the tightrope walker. We're the tightrope walkers, oblivious to the hidden dimensions all around us. The silence stretched, punctuated only by the hum of the air conditioning. I knew I needed to bring it back to something tangible, something that could be tested. So, how would we ever prove that extra dimensions exist? I asked, a note of excitement creeping into my voice. That's the $1,000,000 question, or more accurately, the multi-billion-dollar question, considering the cost of particle accelerators. I winked. One possibility is to look for subtle effects on gravity. Gravity is the weakest of the 4 fundamental forces, and some physicists believe that this is because gravity leaks into the extra dimensions. It's like water seeping through cracks in a dam, I explained. If this is true, we might be able to detect tiny deviations from Newton's law of gravity at very small distances. It would be a subtle effect, a whisper in the noise, but it would be enough. Another possibility is to create miniature black holes at the Large Hadron Collider, LHC. I paused, anticipating the reaction. Now, before you panic, I said quickly, these wouldn't be the kind of black holes that would swallow the Earth. They would be incredibly tiny and short-lived, vanishing almost as soon as they appear. But their existence would provide strong evidence for extra dimensions, I explained. The idea is that the extra dimensions would lower the energy required to create a black hole, making it possible to produce them at the LHC. It's like finding a shortcut through a mountain range. The extra dimensions would make the impossible possible. I took a deep breath, gathering my thoughts. Yet another potential avenue of exploration comes from cosmology. The early universe was incredibly hot and dense, a chaotic soup of energy and matter. The extra dimensions, if they exist, would have been much larger then, perhaps even comparable in size to the 3 we know. I imagine the universe as a newborn. its potential still unfolding. Their presence could have affected the way the universe expanded and cooled, leaving behind subtle signatures in the cosmic microwave background, CMB, and by carefully analysing the CMB, the afterglow of the Big Bang, we might be able to catch a glimpse of the extra dimensions that existed in the early universe. It's like reading the fossil record of the universe, searching for clues from a time long past. I paused again, letting the information sink in. Now let's pause and consider a really mind-bending implication, I warned. If extra dimensions exist, could we potentially travel through them? Could we use them as shortcuts to traverse vast distances in the universe? I smiled, knowing I was venturing into the realm of pure speculation. This is where things get really speculative, bordering on science fiction. The idea of wormholes, or Einstein-Rosen bridges, which are theoretical tunnels through space-time, often involves extra dimensions. In theory, a wormhole could connect two distant points in our universe, or even connect our universe to another universe. Imagine stepping through a portal and instantly appearing on the other side of the galaxy. And this is a big but, I emphasized. Even if wormholes exist, they would likely be incredibly unstable and require exotic matter with negative mass energy density to keep them open. We're talking about stuff that we've never even observed. Matter that defies our current understanding of physics. So while the idea of using wormholes to travel through extra dimensions is tantalizing, it's probably not something we'll be doing anytime soon, or maybe ever. I sighed, a touch of disappointment in my voice. The dream of interstellar travel remained just that, a dream. However, I said, brightening, the mere possibility that extra dimensions exist opens up a whole new realm of possibilities for our understanding of the universe. It could help us solve some of the biggest mysteries in physics, such as the nature of dark energy, the hierarchy problem, why gravity is so much weaker than the other forces, and the origin of the universe itself. I ticked off the problems on my fingers, feeling a renewed sense of excitement. Think about it, I urged. The universe we see, the universe we thought we knew, could be just the tip of the iceberg. Beneath the surface there could be a vast multi-dimensional reality that we are only beginning to glimpse. And who knows what wonders and surprises await us as we continue to explore the hidden depths of the cosmos. It's enough to make you feel both incredibly small and incredibly curious all at the same time. So, where does that leave us? I asked, summarizing. Well, we've explored the possibility of extra dimensions, a concept that sounds like science fiction but is actually a serious area of research in theoretical physics. We've seen how extra dimensions could help us unify the fundamental forces of nature, explain the weakness of gravity, and even potentially travel through wormholes, though that's still highly speculative. I paused, a thoughtful expression on my face. But even with all this mind-bending speculation, we're still left with some fundamental question. What is the ultimate nature of reality? What is space and time? Are there limits to what we can know about the universe? And perhaps most importantly, are we alone? The questions hung in the air, unanswered and perhaps unanswerable. Which brings us to our next topic, the search for extraterrestrial life, I said, changing gears. Are we the only intelligent beings in the universe, or are there other civilizations out there, wondering about the same questions we are? It's a question that has captivated humanity for centuries and one that we are now closer than ever to answering. I leaned forward, my eyes shining with anticipation. 'Cause think about it, even if the universe is infinite, even if there are countless other universes out there, the discovery of just one other intelligent civilization would change everything. It would redefine our place in the cosmos and open up a whole new chapter in human history. Buckle up, I concluded with a grin, 'cause next time we're going on a cosmic safari hunting for signs of life beyond Earth. Who knows, maybe we'll even find something. The thought sent a thrill of excitement through me. The universe was mysterious and full of endless possibilities, and we were just beginning to explore it. So we're looking out at this vast expanding universe, contemplating extra dimensions and potentially universe-destroying bubbles of true vacuum. But what about something a little friendlier? What about life? Is it just us, or are there other civilizations out there, gazing back wondering the same thing? This, my friend, is the question that fuels the search for extraterrestrial life. And it's a search that's driven by a potent cocktail of scientific curiosity, philosophical wonder, and, let's be honest, a healthy dose of wishful thinking. Think about that for a moment. The sheer audacity of humanity, reaching out into the cosmic void, hoping to find a kindred spirit. Now, before we get too carried away with images of little green men, or, sentient space fungi, let's ground ourselves in a bit of reality. The universe is big, really, really big. We've established that. And the distances between stars are equally staggering. So even if life is common, finding it and communicating with it presents a monumental challenge. We start with what we know, us. Earth is, as far as we can tell, a pretty special place. It's got liquid water, a stable atmosphere, a magnetic field to protect us from harmful radiation, and a comfortable temperature range. These conditions have allowed life to not just survive, but to flourish for billions of years. Therefore, a logical starting point in the search for extraterrestrial life is to look for planets that resemble Earth. These are often referred to as Earth-like planets, or more formally, planets within the habitable zone of their star. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. Too close and the water boils away, too far and it freezes. How do we find these potentially habitable planets? Well, we can't exactly point a telescope and see them directly. Planets are tiny and faint compared to their stars. Instead, we rely on indirect methods. One of the most successful techniques is the transit method. Imagine you're watching a distant star. If a planet passes in front of that star from our perspective, transits, it will block a tiny amount of the star's light, causing a slight dip in its brightness. By carefully measuring this dip, we can determine the planet's size and orbital period. Missions like NASA's Kepler Space Telescope and TESS, Transiting Exoplanet Survey Satellite, have used the transit method to discover thousands of exoplanets, planets orbiting stars other than our Sun. Another technique is the radial velocity method, also known as the wobble method. A planet's gravity doesn't just affect the planet itself, it also tugs on its star. This causes the star to wobble slightly as the planet orbits. By measuring the star's radial velocity, its speed towards or away from us, using the Doppler effect, we can detect these wobbles and infer the presence of a planet. These methods have revealed an astonishing variety of exoplanets. We've found gas giants like Jupiter orbiting incredibly close to their stars, hot Jupiters. We've found super-Earths, planets that are larger than Earth but smaller than Neptune. And yes, we've found planets within the habitable zones of their stars. Think about that for a moment. We know for a fact that there are planets out there that could potentially support liquid water. That's a huge step. But liquid water isn't the only requirement for life. We also need a stable atmosphere, the right chemical elements, and perhaps a magnetic field. So how do we determine if these habitable zone planets actually are habitable? This is where things get even more challenging. We need to analyze their atmospheres. One way to do this is through transmission spectroscopy. When a planet transits its star, some of the star's light passes through the planet's atmosphere. Certain molecules in the atmosphere will absorb specific wavelengths of light, leaving dark lines in the spectrum. By analyzing these lines, we can identify the chemical composition of the planet's atmosphere. For example, the presence of oxygen in a planet's atmosphere could be a sign of life. On Earth, oxygen is primarily produced by photosynthesis, the process by which plants and algae convert sunlight into energy. However, oxygen can also be produced by the non-biological processes, so we need to be cautious about interpreting it as a definitive sign of life. Another important biosignature, an indicator of life, is the presence of methane. Methane is a relatively unstable molecule that is quickly broken down in the atmosphere. Therefore, if we detect methane in a planet's atmosphere, it suggests that it is being actively replenished, potentially by living organisms. The James Webb Space Telescope, JWST, is revolutionizing our ability to study exoplanet atmospheres. With its powerful infrared sensors, JWST can detect even faint traces of molecules in exoplanet atmospheres, giving us unprecedented insights into their composition and potential habitability. But even if we find a planet with a potentially habitable atmosphere, we still don't know if it actually harbors life. To answer that question, we might need to look for more direct evidence, such as radio signals. This is where the search for extraterrestrial intelligence, SETI, comes in. SETI projects use radio telescopes to scan the skies for artificial radio signals that could be emanating from alien civilizations. The idea is that an advanced civilization might be deliberately broadcasting signals into space, either to communicate with other civilizations or simply as a byproduct of their technology. For decades, SETI scientists have been listening for these signals, but so far they haven't found anything conclusive. This doesn't mean that we're alone, of course. It just means that we haven't found any evidence of extraterrestrial intelligence yet. The universe is vast, and we've only searched a tiny fraction of it. There are many reasons why we might not have detected any signals. Perhaps alien civilizations are too far away. Perhaps they're using communication technologies that we don't understand. Or perhaps they're simply not broadcasting signals in our direction. Another possibility is that intelligent life is rare. Maybe the conditions required for life to arise and evolve into intelligent beings are so specific and improbable that they only occur on a handful of planets in the entire galaxy. This is known as the rare Earth hypothesis. Alternatively, there's the Great Filter hypothesis. This suggests that there's some kind of barrier that prevents most life from reaching a certain level of complexity or technological advancement. This filter could be anything from a natural disaster to self-destruction through war or environmental collapse. Think about that for a moment. The Great Filter could be behind us, meaning we've already overcome whatever challenges prevent most life from becoming advanced. Or, more worryingly, it could be ahead of us, meaning that our civilization is destined to collapse before we can reach the stars. Regardless of the reasons, the search for extraterrestrial life is one of the most profound and exciting scientific endeavors of our time. It forces us to confront fundamental questions about our place in the universe and the nature of life itself. And it's not just about finding alien civilizations, it's also about understanding the origins of life on Earth. By studying other planets, we can learn more about the conditions that allowed life to arise and evolve on our own planet. So what does the future hold for the search for extraterrestrial life? Well, with new telescopes like JWST and the Extremely Large Telescope, ELT, coming online, we're entering a golden age of exoplanet research. We'll be able to study exoplanet atmospheres in unprecedented detail, searching for biosignatures and clues about their habitability. And SETI projects are becoming more sophisticated, using advanced algorithms and machine learning to analyze vast amounts of data and search for subtle patterns that could indicate artificial signals. The search for extraterrestrial life is a long shot, no doubt, but the potential reward, the discovery that we are not alone in the universe, is so profound that it's worth the effort. It's a quest that embodies the very essence of scientific exploration, the relentless pursuit of knowledge, the willingness to challenge our assumptions, and the unwavering belief that the universe holds secrets waiting to be discovered. And who knows, maybe, just maybe, somewhere out there someone is listening too, and perhaps one day we'll hear their whispers across the cosmos.